A pocket of order is surviving in your room right now, not by breaking entropy, but by riding a flow of energy. That is why complexity exists at all today. Complexity means stable patterns with many interacting parts. Think cells, storms, cities, and your neighborhood power grid. They persist because something hot meets something cold. That difference is steady fuel for structure to form. The universe does not gift permanence freely ever. It gifts gradients you can tap and spend. Tiny systems drink from those gradients and dump waste heat away. Quick mental image: a candle's flame blooms only while air moves. Same rule scales up to planets, stars, and life. Bottom line, complexity survives by surfing energy differences, not stopping disorder. There's a faint afterglow across the sky, like warm dust. That glow is the cosmic microwave background, the universe's baby picture. It matters because it sets the arrow of time. Entropy started unbelievably low, so change had somewhere to go. Heat could flow from hot to cold for billions of years. That one fact opened a budget for complexity. As space expanded, plasma cooled into neutral atoms. Gravity then had time to gather matter into clumps. Photons scattered less, so light could travel and carry information. Slight wrinkles in density made some places denser than others. The contrast was tiny, about 1 part in 100,000, but gravity amplifies tiny advantages into big structures. Galaxies trace those original ripples like ink on water. Example: in real terms, our sun comes from one ripple. That ripple focused gas and later lit nuclear fire. Without a low starting chaos, ripples would smear away. One sentence recap: a low-entropy dawn created lasting temperature gaps for structure. Inside a young universe, forces split like paths at a fork. That split is symmetry breaking, where one rule becomes several rules. It matters because new forces enable new kinds of structure. With different forces, matter can lock into richer combinations. As the cosmos cooled, quarks froze into protons and neutrons. Later, fusion in stars forged helium, carbon, and oxygen. In massive stars, layers stack like an onion of elements. Hot cores fuse heavier nuclei, while cooler shells build lighter ones. Neutrinos stream outward, hauling energy from choked cores. Supernovae then blast those elements into surrounding clouds. Example you can picture: iron rains into a forming nebula. That iron seeds planets and anchors magnetic fields. Carbon dust mixes in, creating sticky grains for chemistry. Numbers help here. Our sun's core burns near 15 million Kelvin. That temperature makes protons tunnel and fuse despite repulsion. Net result: broken symmetries plus stellar ovens supply the periodic table. Across billions of light years, matter arranges into a cosmic web. Dark matter pulls first, then ordinary gas follows those invisible rails. Care comes next because the pull must not be too strong. If gravity dominated early, everything would collapse into featureless monsters. If it were weaker, gas would never gather at all. The universe threaded a middle path where clumps could grow slowly. Dark matter wells deepen while expansion stretches the fabric of space. Gas falls in, shocks, cools, and spins into disks. Supermassive black holes add feedback, stirring and regulating star formation. Example with a number: density ripples started incredibly small. Think gentle hills 1 part per 100,000 high. Over time, those soft hills became clusters and filaments. Quick mental image: bright nodes linked by faint bridges of gas. Our Milky Way lives on one bridge inside that web. So the picture is: balanced gravity sculpts a scaffold for complexity. Now zoom tighter to a quiet, steady star like ours. A long stellar lifetime is a priceless grant of time. It matters because slow, reliable light sets a stable stage. Planets can orbit, cool, and cycle without violent mood swings. Hydrogen fusion releases energy with astonishing thrift. The sun turns mass into light with careful efficiency. Magnetic fields braid and relax, but the core stays steady. That steadiness limits flares and keeps output within narrow bands. Planets then receive a nearly constant energy drizzle for eons. Example in real terms: Earth drinks about 1 kilowatt per square meter. Day after day, that flow drives winds and water. Chemical cycles can iterate, fail, and try again. Rule of thumb: consistency beats intensity for building complexity. Net result: long-lived stars rent stable light, letting planets run long experiments. Shift from stars to the chemistry written in tiny angles. Complexity needs flexible parts that still lock with precision. Carbon provides that sweet spot with 4 cooperative bonds. It matters because such geometry stores and processes information. Carbon chains bend, branch, and form rings with ease. Hydrogen and oxygen attach, creating a reactive but stable toolkit. Water adds a magic trick with polar attraction. Molecules meet, stick briefly, and then separate on cue. That timing lets reactions search, assemble, and edit structures. Example you can feel: DNA backbones are carbon highways. Bases are ring stacks that zip and unzip underwater. Proteins fold as side chains test many shapes at once. Numbers help: a single cell holds billions of carbon bonds. Those bonds switch states without shredding the whole machine. Bottom line, carbon plus water make a programmable wet computer. Complexity does not grow in calm thermal equilibrium. It blooms in traffic where differences drive motion. The key is a flow that lowers gradients while making patterns. That definition captures everything from hurricanes to brains. Stakes are simple. Without flows, patterns fade into lukewarm sameness. A gradient pushes matter into cycles and feedbacks. Vortices, reaction fronts, and membranes appear as shortcuts for dissipation. They persist only while the flow supplies fresh difference. Living cells do the same trick with chemistry. They import low-entropy nutrients and export heat into surroundings. Enzymes speed the traffic, and genes keep useful detours. Example with a number: Earth dumps enormous heat to space. Think tens of petawatts streaming away every clear night. Local order rises while global entropy increases faster. Quick mental image: a whirlpool sharpening while the river keeps falling. What to remember: complexity is a heat engine with memory. Here is the awkward question: why are the knobs set just right? Some constants sit in ranges that welcome complex structures. The idea is anthropic reasoning, selection shaped by observation. It matters because brains only appear where brains can form. Variation across regions could span many constant values. Observers then count from places compatible with long chemistry. A second view is evolutionary. Universes might spawn with tweaks. Fruitful settings would host more black holes or long stars. Either way, selection filters what we can ever measure. Example in numbers: initial lumpiness could not be extreme. If ripples were 10 times bigger, galaxies would crash early. If 10 times smaller, disks would rarely form stars. Dark energy must also be tiny yet positive. Too large and clumps tear apart before lighting. Net result: we notice a Goldilocks set because noticing requires it. Step back to the opening claim: order rides on moving gradients. That includes you, your devices, and every living leaf outside. We borrowed a candle's rule and applied it to galaxies. The same physics stitched atoms, stars, and minds into one story, and the story is still running while the flow lasts. I hope this gave you a clear mental handle. If this clicked, share it with one curious friend. For now, breathe and notice the quiet engines around you. Calm recap: complexity exists because the universe funds it with gradients.